Welcome everybody to week 3 of GatesAir's virtual events webinar series. Today our very own Joe Seccia will be delivering a message about cloud delivery of NextGen TV ATSC 3.0 services to transmission sites using SRT. Before we begin, let's take just a quick break. You'll see the countdown. When the countdown timer ends, we'll begin the webinar. So just sit back, relax, and we'll just see you in just a few minutes. Hello everyone and welcome back to the GatesAir Connect Virtual Events webinar series. This is Teresa Crippen, Global Events Manager for GatesAir. We really appreciate all of you connecting with us today during today's webinar. If it weren't for shelter-at-home quarantine orders, many of you here on this stream would be returning home from the NAB show this week. In place of many canceled face-to-face events, we have lots of interactive content for you to see over the next few months with our virtual event series. In today's webinar, Cloud Delivery of NextGen TV ATSC 3.0 services to transmission sites using SRT, we have our principal architect for our TV product line, Joe Seccia, who will tell us all about the ATSC 3.0 as a cost-effective IP distributed platform implementation of cloud-based content delivery using advances in SRT. We'll have a question and answer session at the end of the presentation, and we encourage you to type in any questions you might have in the Microsoft Teams Q&A panel. We'll be answering those questions in a first-come, first-served manner, so feel free to enter them as soon as you think of them. I will post a quick announcement once Joe begins to let you know where that panel is. Without further ado, let's start the webinar. Please welcome Mr. Joe Seccia. Joe?
Okay, thank you, Teresa, and welcome everyone out there in the virtual world. Yes, it was a little strange not having NAB this year. I guess everyone's kind of, caught up with that fact. So what I'm going to present today is a project that we had, talked about to actually implement at the NAB show and talk about. So what we did is we did a not a compromise, but an alternative method, and we'll explain to you some things here about using cloud to deliver ATSC 3 services via secure, reliable transport mechanism. So let's begin. The motivation for this is that, evolving to next generation TV or ATSC 3.0 is unlike the NTSC, the DTV conversion in several ways. With the lack of spectrum and the repack that just we're winding down on, there's going to be, you don't get another channel to do ATSC 3.0. So there's going to be a lot of channel sharing with host and guest stations, and it's likely to involve disparate locations of contributors and transmissions, because you're going to be partnering with the station across town, to host your signals, while your one station hosts the ATSC 3 signals and the other station's got to host the ATSC 3 stations standard signals for a while. So there's going to be signals going between stations, and the architectures have to potentially change. So there's been a lot of architectures and ideas floated regarding delivering NextGen TV to consumers, i.e. from transmission sites. And we still have the classic single transmission site. We have idea floated of a single transmission site augmented with SFN fillers, or a completely distributed SFN architecture, and perhaps gap fillers as necessary in either of those scenarios. So the change to shared infrastructure brings opportunity to evolve distribution of transmitter sites. It seems that the classic one studio, one transmitter site paradigm is shifting by necessity because of the sharing. High-speed connectivity is on the rise everywhere, and broadcasters are moving to cloud encoding today. It's ongoing. It's basically an operational expense versus capital expense move of dollars, and hopefully cost savings. And also by doing that, your hardware doesn't necessarily go obsolete. You get a software update based on software as a service or contract, and you're always on the latest platform, and it's an operational expense. So it's a way to keep up to date cost effectively. And a lot of powering this is commercial off-the-shelf server hardware today is extremely powerful, which is what enables it. You see a lot of equipment now that is no longer a dedicated piece of broadcast gear. It's a commercial off-the-shelf piece of hardware, which lends itself to be put in the cloud. And also the COVID-19 is really teaching us the extent of things we can do with broadband connectivity, and accelerating plans, broadcasters' plans of moving to the cloud. So why secure reliable transport, or SRT? First of all, it's secure. It has the capability to encrypt content in accordance with AES 128 or 256 standards. It's reliable in that it recovers from severe packet loss, and the transport mechanism dynamically adapts to changing network conditions. Now, this is a little bit more apropos to the original vision of SRT, which was to deliver, video over public internet. So, I'll talk about our case here is a little bit different, but it was designed for high quality, secure, low latency transport of video over public internet by modifying UDP, the UDP-based data transfer protocol, or UDT. So, why UDP? TCP guarantees delivery, and that's really what we want. But control of latency and buffering are concerns in the TCP space. So UDP gives us high throughput and low latency, but no delivery assurance. So what to do? It's like we're trying to force fit a solution into a mechanism that isn't really built for it, but it does work with all the appropriate actions. So SRT incorporates innovative technology to overcome UDP's best effort reputation. Also, SRT is scalable. We can do point to multi-point. I've got a couple diagrams later. It's firewall friendly. And also it's open source. The community can extend and enhance. what's in there, and if there's any development that a SRT vendor makes to the core, they're obligated to update the open source. The source, if they update source code, they have to update the community, so everyone benefits by an individual's development. And the SRT has the alliance formed, by High Vision and Wowza Media Systems. They're the originators of the SRT Alliance, and there's over 200 members of the SRT Alliance. And I just grabbed a few companies and names that are members of the SRT Alliance and are either putting SRT product on the market or using SRT in some way in what they do. And you just in the broadcast space, there are plenty of companies here that you may recognize. So it's very highly supported ecosystem. So some background on SRT. It's a connection-oriented protocol. It provides transport of media and control messages. So this diagram up above shows an SRT source device and an SRT destination device, and connected, via some connectivity, i.e. cloud, or doesn't have to be cloud, can be, a wire, a fiber, but, we're talking about cloud here. So in that respect, either the source or destination, either device can be a caller, a listener, or they can both be in rendezvous mode to establish a handshake. And it's independent of source and destination in the caller listener. So the source can call, set up to be the caller to call the destination device to initiate the stream, or likewise the destination device can be the caller, where the source is set up as the listener. So either one can be set up to call and initiate the connection. So it's independent of source and destination. It's very flexible in that way. And rendezvous mode is where they set up to talk to each other and establish connection, as needed. It's flexible and scalable, and here we're showing that you can have this diagram is from the from SRT documentation, but it shows multiple sources and the original vision of SRT having encoders such as video encoders going to the cloud through an SRT tunnel or tunnels, and then having a gateway server at the destination, and then having that content split back out to its relevant destination device, be a media platform, or the example here, a digital signage server or an IPTV server. In our case, this could be multiple broadcasters going through an SRT tunnel and then coming out in different transmitter sites. So consider it transmitter site 1, 2, and 3 on the right, and source material relevant to each broadcaster on the left. And so we can support multiple sources, multiple destinations, and we can do down below, we can do a single source through an SRT cloud tunnel and come out at multiple destinations. So this would greatly support via cloud, several SFN sites out there for ATSC 3.0. So instead of having to architect microwave or whatever paths, you could do this from growing and more readily available high bandwidth connections out there to any given transmitter site. So ATSC3 has a transport standard, the A324 STL standard. It originally was documented as multicast only to put out IP and multicast packets. So RTP, UDP multicast. And some of you have worked with multicast before. Sometimes in the plant, it's easier because you control the plant and you can map a switch port to allow multicast from port A to port B. But sometimes getting multicast through an infrastructure can be problematic. I've helped customers deal with that, and it's surprising that an internet service provider didn't allow it. They blocked it. They allowed multicast step 1, it still didn't work. Well, they were blocking the RTP header. So you have to work through things like that when dealing with multicast. But I think education and so forth is growing out there, that it's not feared as much as it once was. There was a lot of fear that multicast would flood anything and take things down. but properly handled, that's not the case. But there was a recent update to the ATSC 3 transport standard to add unicast to accommodate for smaller internet providers that may have the difficulty I just spoke of above in properly provisioning for multicast traffic. So even though it's unicast, it's still UDP based, similar to SRT. And on the security side, the A324 transport is evolving. However, the security there is rooted in norms of the broadcaster having physical presence at each end of the studio transmitter link. So this isn't necessarily cloud friendly, but probably could be, with appropriate provisions, be adapted to cloud. And it's not encrypted, it's authenticated. So there's authentication going on in this security link, not encryption. So it's designed such that you can be alarmed or take appropriate action if the link is compromised, but it's not encrypted. That said, the data that goes across the A324 transport is really only usable by an ATSC3 modulator or exciter. It's not content in the clear like video. It's been highly processed, and in fact, it's gone through one of the first steps of modulation to get the data into baseband frames. So it's not like somebody's going to tap into this link and be watching your television program. So that's why it's authenticated, not encrypted. However, if we go to cloud, we really might want to encrypt that. So here's what we had planned to do at the NAB show that was canceled. We were going to have Harmonic generate content in the cloud and encode it, dash package it, send it to Triveni Digital to be route encapsulated, add signaling, and then put it through a scheduler, an ATSC 3.0 scheduler / gateway, and then send it to our Intraplex Ascent SRT platform. Have that all housed in the cloud, Harmonic's cloud, and bring it down at the Harmonic booth at the NAB. So this, was going to use a pretty good amount of bandwidth of the Harmonic cloud instance. So that changed a little bit from what we originally planned to do, but nonetheless, this was the idea, to house everything in the cloud and bring down our ATSC3 transport through SRT to Harmonic, the Harmonic booth. And then we had set up inter-booth links from the Harmonic booth to the Gates Air booth, where we'd have a exciter low power transmitter, and also an interlink from the Gates Air booth to the Triveni Digital booth, where they would also have a low power exciter transmitter. So this didn't happen because the show was canceled. So what we did is we worked up an alternative to just prove the concept here. And shown in this diagram from Triveni Digital to help show what we're going to do is at Triveni, here in the towards the left center, they have their guide builder platform providing services. So there's services coming in HEV encoded, or they also have a live source simulator that they can use and bring it into their guide builder and put together the appropriate signaling and announcement, and then route encapsulated or route encoder, encode the information coming. Then it went to a broadcast gateway. So unfortunately, this diagram is just a hair confusing because it has ATSC1 and ATSC3. So follow the ATSC3 path on the bottom, where we come and we go to a gateway, a scheduler framer device, and baseband frames and STLTP are sent to an exciter modulator. So that path at the lower right, where it's baseband frames and STLTP, we're going to take that STL, that stands for STL transport protocol. We're going to take that STL transport protocol and we're going to put it into an SRT device. So at Triveni, we shipped an Ascent Media platform to Triveni's office in Princeton, New Jersey. They connected the scheduler gateway to the Ascent device, and through their firewall, we poked a couple of holes in the firewall to be able to get the data through internet to our facility here in Mason, Ohio. Our facility here, we have an outside internet, so we didn't go through our corporate firewall here. We just went through straight outside internet and came in. Although the service doesn't have that much bandwidth, this was the plan to go to the internet, bring it down, and then take the STL-TP out on the receive end of the Ascent Media Platform and SRT, take it to an exciter, and radiate in the laboratory. So this is what we have set up and what we did some experimentation on to, prove the concept of the cloud delivery here. So there's some imperfections in this network. So secure, reliable transport is the one mechanism that helps with all those imperfections. And then if the SRT mechanisms aren't enough, if we still have an error, occasional error or two, we can add SMPTE 2022 forward error correction to the link by using the 2022 error correction that's specified in ATSC's 324 STL standard. And then we can also do some network diversity to help mitigate any imperfections in the link. So now SRT's algorithms within those are measures to mitigate the effects of delays, jitter, and packet loss. And we need to remember that the SRT mechanism was designed to deliver live video and so forth, and consider yourself at home with home quarantines and all the extra viewing that's going on with delivery platforms such as Netflix, Amazon Prime, and so on. If your link changes, the algorithms that they have in place can throttle back and throttle forward, and you may lose some resolution. You may get a freeze frame or two, but your experience is still maintained. So within SRT, large buffers help, but they're at the expense of latency. And when we're in a live television domain, we want to minimize latency. So that sports events and so on, that everybody gets it as early as possible. And SRT implements a mechanism that recreates the input signal characteristics on the receive side. It serves to reduce the need for buffering. So you can see on the left, the source might have characteristics like that, and then shown in green. And then through the network, the imperfect IP network, we have a lot of time delays and bandwidth changes, but on the output side, we essentially receive what was put to the input. And so some other SRT terminology on the transmit side, because SRT has the ability to resend packets from within the buffer. I'll mention a couple things later. So if there is a latency set up and the network characteristics, the SRT algorithm can resend packets that were dropped. So within SRT, there are handles here to show you that, packets that were retransmitted from the destination device said, I didn't receive this packet and I need it. The sender can resend it. And as long as it's within the buffer, we can present it on time. So it's somewhat like TCP in that way. And then, drop packets, of course, are number of packets reported missing by the destination device. And, they may be recovered by retransmission by the source. But if it's too late, it'll end up being a skipped packet at the end. So, like I said, these do not necessarily result in video artifacts in the SRT original concept here. On the receive side, we can look at lost packets, with the number of packets reported missing by the decoder, and skip packets. And this technology, this terminology is just a little bit different than you may think of in terms of drop packets from, or lost packets from, if you've done any data mining with Wireshark or so forth, and RTP, to say, oh, this packet didn't arrive or this packet was out of order. So you know, the decoder can say I've lost a packet, but it can be resent by the sender. However, if those resent packets arrived at the receive side too late or never at all, it's logged as a skipped packet. Okay, so that's what would provide the STLTP receiver or the exciter a problem, because it needs to have all the data. So, you know, if the time to play the packet is passed, it's reported as skipped. And in the SRT paradigm, this will result in a video artifact, but in the ATSC3 paradigm, it would result in a modulator, you know, stop restart. So now on the SRT link tuning, we have here's the passphrase for the security. It's used for the AES encryption. So we had a simple passphrase in there, Intraplex SRT. You could put in whatever passphrase there fits the standard. And also, if you were going to deploy this, I think one of the criticisms is that the passphrase security is at risk because the passphrase could get out or could be compromised. Well, you as an organization need to have a standard in place to where you can generate these passphrases and change them occasionally, and people in the know would have control of them, and people that don't have a need to know would not be exposed to them. So round trip time. So if you've ever done a ping, you get a round trip time. This is used to help manage the network, and it's the round trip time for packets on the link between the sender and the receiver. And then there's a multiplier. We need some buffer. So there's an algorithm for the round trip time multiplier that controls the stream latency factor, and it can be set with an estimated packet loss rate for the link. And see, we've got the packet loss rate here very low because we really can't tolerate any. So the round trip multiplier increases to give us, plenty of headroom here. And then the latency, of course, is the result of that multiplier and determines how long to keep packets for retransmission. So as I was speaking about, the SRT paradigm for streaming video involves managing factors of round trip time, latency, link bandwidth, and dynamics, as well as encoder rate. It works well for the streaming video world, and as we use it in our Intraplex product line for audio, so that the you can throttle the bit rate back of the encoders to manage the bandwidth, but we don't have that luxury in STLTP. So the SRT guides implementers on how to use ping or other network tools such as iPerf and so forth to get these data points to set up the network appropriately to achieve desired link performance. Well, in ATSC 324, we know what the bit rate is. It's constant bit rate, and that bit rate is set by the physical layer parameters that are set up in the scheduler for your broadcast. With a certain constellation size, let's say 256 QAM, and a forward error correction methodology to give you a threshold for the receiver to drop out. Equivalent. So as an example, an equivalent bit rate in ATSC A324 with modulation settings to get to a 15 dB signal to noise dropout at the receiver that's similar to 8 VSB, leads to a STL link bandwidth on the order of 26 megabits per second. That bandwidth is constant unless you change your parameters on a daily basis or some sort of regular schedule basis. That bandwidth is going to be constant bit rate. So the good news is we know what it is, and we can lock down a QoS agreement and desired overhead with a provider, cloud provider. So it's not going to vary on us. We know what it is, and we can design to it. And the important thing here I've noted in red is that this link is intolerant to packet loss. So unlike if you were doing streaming video or audio, where you might get a hiccup in the video and audio, here in a packet loss at the final end is really not good. The exciter modulator needs to have no packet loss whatsoever. So If we're getting a little bit of packet loss, or to help mitigate with an imperfect link, ATSC 324 specifies SMPTE 2022 forward error correction. And here in the SRT tunnel with the Intraplex Ascent platform, via UDP multiplexing, we can add in the SMPTE 2022 forward error correction into the link. So shown here is the address for the actual data. So on port 8007 is our actual data at 9.4 megabits. And then we've got row and column forward error correction according to 2022 at 2.3 megs and 1.5 megs. That adds to the link, overhead of the link, but we can then use this to account for an error that the SRT could not account for. So a little bit SRT is belt, and the 2022 could be suspenders, so to speak. So by the UDP multiplexing, we can see at the sender, repeat of the last slide, you've got the data coming in, and at the receive side, we have mapped this to a different multicast address, and we're sending it to the exciter and getting that data out. And you can see here from the exciter screen in the lower left that we've got an error-free link. There are no recovered or lost packets, and we see the SMPTE 2022 matrix data coming in to help in case it's needed. So a very good feature of the Ascent. Now, if the SRT algorithm itself plus SMPTE 2022 is not enough, or you want to actually have it as redundant as possible, we can use a concept we call dynamic stream splicing, which you take SRT device and you run it through two different networks. So you've got network diversity here. So in the cloud instance, you may have cloud provider 1, WAN 1, and cloud provider 2, WAN 2. So you've got time diversity between the two links, and this can, so giving link diversity. For one link has a dropout, the other link can fill in. So this can achieve hitless operation with packet and network losses in accordance with the backbone of SMPTE 2022-7. So we have all the SRT mechanisms, 2022-1 FEC, and 2022-7, seamless stream splicing capability to give us as much robustness as possible across the internet. And so what we have here is the output realized in our Mason, Ohio facility lab, where the well-known Big Buck Bunny program was being sent from New Jersey, and I'm showing it being decoded here, received and decoded on Treveni StreamScope XMMT, and also received on LG TV in the lab. So we've essentially achieved the cloud delivery between New Jersey and Cincinnati, Ohio. So I'd like to give a lot of thanks here for this program, because when the NAB was canceled and we had to figure out how to do this, we had to get with people on each side where we would normally collaborate at the show. So Dave Catapano, Kota Serratu, and Ralph Backhofen at Triveni provided all the help, and had a lot of calls back and forth of the links dropping. But the reality is that the Triveni team was using the stream for their own testing and purposes, while I was trying to have a perfect link. And so when the link went down or data went away, there's a call to Triveni, what's going on? Oh, well, we're moving that. Okay, so it wasn't the link, it was somebody using it. So you have a little bit of inefficiencies of working remotely and trying to multi-purpose equipment, but nights and a couple of weekends, it was flawless when it wasn't being touched on the other end. So, and on the GatesAir team, Gavin Gunler, software engineer behind the Ascent product, and Kayer Preek, our vice president for Interplex products, was a great help in putting this together. And at Harmonic, Joel Wilhite kind of launched this off and said, hey, you know, I've got a cloud instance and I've got an idea, and we put it together. I've got some further reading here for you because there is some discussion out there in the streaming world of different approaches. So what we have is, you know, on one end, there's a proprietary protocols, and there's a new protocol on the other end called RIST, real-time internet streaming, and SRT is kind of in the middle. So, you know, RIST is, so on one side, we've got proprietary. RIST is attempting to be, you know, more of a standards-based vetted approach, and SRT being open source is kind of in the middle of the road here. So last year, NetInsight did a nice paper on this, and this will be available later for you. So don't worry about, you know, writing all this down or whatever. So I just think it's interesting reading on the concept, and so I'd like to thank you all for attending today, and we will attempt to try to answer some of your questions.
Thanks, Joe. Before we get into the Q&A portion of the program, I have just a couple of announcements. Go ahead and put in your questions into the Q&A pane of the Microsoft Teams panel, and we'll answer those in the order that they were received. This webinar is going to be recorded, or it has been recorded, so it will be available at the same link that you received to sign in. It will also be available on gatesair.com and our YouTube channel. In addition, we'll be adding this webinar to our educational video library at gatesairuniversity.com, which is our online hub of lessons and webinars about broadcast engineering. Also, if you didn't know, this webinar, like all of our webinars at gatesair.com, qualifies for 1/2 SBE recertification credit, identified under Category 1 of the SBE's recertification schedule. For more information, please visit the certification section at sbe.org. Now on to the questions.
I just want to say about this slide here, this picture, this is actually in a neighborhood close to where I live. I just had to stop and take a picture. Please don't steal my roll of fiber.
Wow, does that really happen?
Well, people will steal it because they think it's coaxial cable and they can take the copper out of it to a metal recycler or whatever. And just wondering if this, so don't steal it because it's not copper. It's fiber, but you know, I imagine that this spool of fiber wasn't inexpensive in and of itself, but you can't take it to a fiber recycler and get money if you're a thief.
Right, that's unfortunate.
Teresa, it looks right now we have no questions in the queue.
Okay, well,
Very thorough, Joe.
Yeah, very thorough. Thank you. Well, since there's no questions, I think we'll go ahead and wrap up. So thanks, Joe, for taking the time out to talk about.
We just got one here. It's
very
simple. Yep, is Ascent available now?
Yes, Ascent is a you know, current product of the our GatesAir Interplex product family.
Can I chime in on that? This is Kayur Parikh. Yeah, so the capability of the Ascent Media Gateway, which Joe was referencing to, will be available GA end of July.
All right, are there any other questions out there?
Yes, we've got another one here. What are the estimated costs of the equipment?
Of the Ascent Media Gateway. So we've not released those pricing yet, but if you're interested in getting a preview of those prices, please reach out to your regional sales manager, and we can provide you a confidential pricing that we would expect the product to be when we do a GA.
All right. What about a DVB T2 distribution with Ascent?
Yeah, sure. You know, the thing is that the SRT is essentially transporting UDP at a very base level. So DVB-T T2 transport stream or T2MI embedded into a IP stream can then be transported with Ascent and using the SRT technology. And there's another question I see: is it possible to transport stream over SRT between studio and transmission plant using a public network? Yeah, absolutely. Only not it's not ASI or 310. It has to be embedded into IP and UDP, and then it certainly can be transported.
Okay, we've got another one here as well. In an SFN, is there a need for a Ascent unit at each transmitter? For an Ascent unit at each transmitter, sorry.
Well, you need an Ascent unit at any, you need one at the transmit end, send end, and receive end. So depends on, your distribution network. But in an SFN that doesn't have connectivity, say a microwave connectivity to your studio or whatever, yes, you need an Ascent unit at each transmitter site, connected to, your cloud provider or whatever your provider is of the path there, or the bandwidth connection there. And so the answer basically is yes.
Okay, we've got another one here. What is the opinion about using the solution for other digital TV standards such as DVB or ISDB?
Well, if it's for either of the standards, DVB-T, T2, where DVB-T and has makes use of MPEG-2 transport, and T2 uses an adapted version of that called T2MI. Those are MPEG-2 transport based mechanisms. So and also ISDB-T making use of MPEG-2 transport mechanism that is referred to as broadcast transport stream. Those simply need to be embedded into IP, so transport stream over IP, if you will, and then that IP payload can be transported using Ascent and SRT, and then at the other end it's de-embedded and straight to the transmitter. Now at the head end, if you've got transport stream and you embed it into IP so that the Ascent media gateway can ingest it and transmit it over SRT, at the receive end, since all of our modern platforms are IP enabled, you don't need to come out of Ascent and IP, then convert back to transport stream on ASI. You can take that IP directly into the transmitter then. So you you don't have to do that one conversion step at the transmit site.
All right, we've got one more. Would this be applicable in a centralized master control application?
Not sure of the application within master control. Perhaps the person asking the question could elaborate a little bit more. It's basically for distribution out to transmit sites. But it could be used, you could put an Ascent platform at master control that's receiving from the cloud provider and have confidence monitoring at master control to know that the link's good. But your link at master control may be different than your link out to a given transmitter site. So be careful not to be fooled that I've got good link at master control, and you may have a link issue out at a disparate transmitter site. So that would be a caution I'd have there.
Okay, can this product handle more than one SLT per broadcast site?
It's agnostic. of SLT. So whatever UDP payload that you decide to put in, it will transport. So it does not inspect or parse out SLT for broadcaster 1 and broadcaster 2. So in that sense, yes, it's applicable.
All right. What about using Ascent for contribution feeds with high bit rates, typically using light compressed high bit rate video?
Well, CARE, perhaps, as long as it's, bandwidth, within the bandwidth constraints, in this demo, we use like 9-10 megabits per second, but in a real system for ATSC 3, you're going to be on the order of 20 to 30 megabits per second. And if you've got more services, it can get, upward of that quickly. So as long as the cloud provider can provide that bandwidth, I guess it would be up to, can the product platform take in and ingest and handle that much bandwidth? I believe the answer is yes, but I'll let Kay answer.
Yeah, no, I think you covered the points. Yeah, so the platform, there is no inherent limitation. We use commercial off-the-shelf computing platform for scalability just for that purpose, and it can be virtualized, so you don't have to get it on our own branded server. You could run it on your own platform if you want to, and yeah, I mean, inherently the capability does not have limit, although we have tested it up to 50 megabits per second here in the lab. So I don't see a problem on the contribution side as well.
Okay, is it possible to receive the signal directly on a Gates Air transmitter? And if not, will it be in the future?
That's a good question. We've talked about that here. It is potentially implementable directly on a Gates Air transmitter, and it's under evaluation. And so the current answer is no, and the future answer is we're looking at it. What we need to do is, we need to implement an SRT instance within the transmitter control platform or the exciter control platform, and there needs to be appropriate resources in the platform to be able to do that.
Well, it looks like our questions are drying up here. I've got an empty queue at the moment.
Okay, with that, we can just wrap up. If you have any additional questions, you can contact us directly. Thanks again for everyone for attending today. And again, you can see this presentation again at gatesair.com or on our YouTube channel, or simply by using the same link that you used to view the live presentation today, or also gatesairuniversity.com, which has lots of valuable content to view. Join us again Tuesday, April 28th at 10 a.m. for our next virtual event webinar, and that will be DAB, Complete Solutions for Total Network Deployment. Our very own Ted Lance will examine the advances in compact, cost-effective DAB transmission solutions, ideal for deploying across diverse geographies. He'll also cover new compact gap fillers, multi-carrier systems, and higher power liquid-cooled options that arm broadcasters with a full array of solutions that can be tailored to specific network needs. For more information about that webinar and many more coming up in the next month and a half or so, please visit gatesair.com/v-events. If you have any ideas for future webinar topics or course materials for Gates Air University, please let us know directly at marketing@gatesair.com, or you can email me directly at tcrippen@gatesair.com. Thanks again for everybody for attending this Gates Air Connect virtual event. From all of us at Gates Air, stay safe, stay happy, and let's stay connected.